Gavin Buckingham, an associate professor in the Department of Sports Science and Public Health at the University of Exeter. I'm a cognitive psychologist by training. This isn't my first Illusions of the Fortnight talk. I've given talks on weight illusions before, which are going to be a big feature of what I'm going to talk about here today as well. But here I want to talk about some of the work I've been doing with virtual reality, which has really driven where my career has been going over the last 5 or so years, I would say. Now, virtual reality, which almost everyone will be aware of now in some form or another, would formally be defined as interacting with a computer-generated environment. And for me, it's this word interacting that really is kind of a key part of this whole narrative here, right? You can be in a virtual world, you can watch videos in a VR headset, but you're not in virtual reality until you can have some interaction with those. And the way that interaction has moved over the last few years has kind of really changed the whole ecosystem of virtual reality. Now, virtual reality is developed, I would say, largely as a consumer technology. It's a gaming system with Meta Quest 2. Here, this person is playing Beat Saber that I'd imagine many people have had the opportunity to play with before. Still, incidentally, the best thing you can do in virtual reality as far as I'm concerned. But it's developing a life as a training tool. Here we have Resol, that is a training simulator that is purchased by a bunch of Premier League football clubs. And there are all these reports of players during the pandemic who weren't able to go to training but were able to play in VR and do all of these sorts of things. Virtual reality of some form or another has been part of medical training for quite a while now, and particularly in the world of orthopedics in North America, there's a really big push to include virtual reality into its core training programs to streamline some of the processes. And we're sort of at the stage now where virtual reality and remote operation, teleoperation, are becoming a sort of a linked up part of everything together. Here we have the tactile tele robot that is sensing the forces applied to this ball that's being picked up with those little blue pads on the fingertips and sending those directly to the wearer of this haptic glove, so you can feel in virtual reality and not just see, which is a pretty exciting next generation of how this technology is going to be emerging. Of course, the virtual reality is trying to do its own thing, and it's trying to reinvent itself largely through Facebook and Meta as a social platform. And whereas this idea of a metaverse isn't something I'm particularly interested in, the feeling of being in a room with someone in virtual reality is really quite profound and starkly different than sharing a Zoom call with someone. You really are sharing space and feeling co-located, and can move close or further away from people and be expressive in a way that's quite hard to do in the flat world. And we're almost coming full circle here, where we're seeing virtual reality experiences, that you need quite a lot of space for, just to simply replicate things that you could do in the physical environment. But I guess critically with friends who are based halfway around the world, and that's pretty exciting in this new geographically distant world that people are living in here. I, however, as I have mentioned, am a scientist, and I'm interested in virtual reality from a scientific perspective. My first ever grant was from the Experimental Psychology Society to develop a virtual reality research program, which, it turns out is actually quite a cheap thing to do, rather surprisingly. And the hook for doing stuff in virtual reality is that you have sort of total control over many of the environmental factors that are really of interest here to scientists, particularly perceptual scientists. So control the visual inputs, control some of the auditory inputs, put things in conflict that just simply wouldn't be easy or possible to do in the physical world. And while people in the world of perception have been playing with things that would be a bit like virtual reality for, many decades, really, with half silver mirrors and things like that, the virtual reality headset has become a whole different way to interact with things in a really ecologically valid way, while at the same time precisely measuring movements of the eyes and of the hands. Right, so as I mentioned before, I'm a cognitive psychologist who's interested in human perception and human motor control, and I guess that means what I do is I make people come into the lab and pick things up and tell me how heavy they feel. That's kind of my core research program. And I've been doing this research in the context of something called the size-weight illusion, which some of you might remember from my previous talk here. It's basically the simple premise that it's not just the object's mass that affects how heavy something feels when it's lifted, but also its volume will affect how heavy it feels. Such that if you take a bunch of different objects and adjust them to weigh the same amount as one another, here I've got 3 differently sized cubes that are all adjusted to weigh 700 grams. When people pick these things up and give a number to represent how heavy they feel, they'll typically report the big object as feeling really quite light, whereas the small object, even though it's the same mass, will feel substantially heavier, up to twice as heavy in some cases. So it's a really powerful illusion that's been floating around the perceptual ecosystem for approaching 150 years now. So it's something that's interested scientists for a long time. So we have this premise here that the size-weight illusion, that an object's volume affects how heavy it feels, such that small objects will feel less heavy. Will feel heavier. No, I've got that the wrong way around. Will feel heavier than equally weighted large objects. And this is thought to be something to do with expectations. So when you see something in the environment, you have an expectation about how heavy it's going to be. And because big things usually weigh more than small things, you tend to expect that the big thing is going to be heavier than the small thing. So when you pick up that small object, you're feeling it as, ooh, that's heavier than I expected it to be. And that's the perceptual experience. So, maybe a bit like a sort of adaptation process, a bit like coming inside to a warm house from a cold day and it feels swelteringly hot, for example. Not a great analogy, perhaps, but one that gives you a sense of what it might be feeling like for the person. So what do we mean by expectations, though, right? Well, we see the size of something in this case, and we get an expectation about how heavy it is. But you can experience the size of an object through a number of different modalities. You can see an object is big, or you can feel that an object is big, or you can see and feel that an object is big when you're picking it up. And people have been quite interested in tackling, through this mechanism of the size-weight illusion, which of our senses we trust the most in this context, which our vision or our sense of touch would give us the highest level of expectation that something is going to be heavy. So the foundational study here is from 1993 by Ellis and Lederman, a really nice paper where they looked at size-weight illusion-inducing objects in a few different conditions, either picking up on a tray, so there's no haptic information about the size of the object, or picking up on a string. So there's or picking up with the eyes closed and feeling it, or eyes open and feeling the size of the object as well. So you can kind of imagine all of these situations here. Now, this is a very 1990s graph, so I won't get too stuck up on it, but I'll try and step you through it a bit here. The steeper the slope is the bigger the illusion. That's kind of the only key takeaway from here. And what they found was this situation where you had your eyes closed, but you're feeling the size of the object when you're picking it up. That yielded a much, much larger size-weight illusion than if your eyes are open and you're lifting up the object on a tray. So you're only getting the visual size cues. And perhaps most crucially, the situation where you can see and feel the size cues didn't give any different illusion to the haptic-only condition. So they concluded that the size-weight illusion is a primarily haptic phenomenon, which, okay, fine, makes sense, but is quite, conflicting with what a lot of people would believe about the belief we have of our senses. It's kind of a bit of a flip around of the way most multisensory research paradigms tend to pan out. So I was quite interested in tackling this in a kind of different context with this grant I got from the Experimental Psychology Society, where we were able to put together my motion capture system with a newly released virtual reality headset, at this time the Oculus Rift DK1, and track live the positions of different objects and play them through a virtual reality headset to the observer. So here, what you can see is this participant is moving these objects around and seeing these objects as they're being moved. But the objects that they're holding are of different sizes than the objects that they're seeing. So we can create this incongruence between what you are seeing and what you are feeling that would be really, really challenging to do in the physical environment. So we set up an experiment pretty much exactly like you might be imagining how it goes. The participant would be put in this VR headset and they would reach out and pick up the object and give a rating about how heavy it felt, giving a number, for example. And we did this in 3 different blocked conditions. Condition 1, where we have pretty much a matching of the virtual world and the physical world. 3 differently sized cylinders that look as if they are 3 different sizes. So congruent visual and tactile information that people are picking these objects up and experiencing how heavy they feel. Condition 2, where things get a bit more interesting, where we have 3 physical sizes of objects. So they all feel different sizes, but they look as if they have the same size as one another. So only a haptic size difference. And the final condition, where we have 3 identically sized objects. So they feel as if they have the same size, but they all look as if they have different sizes in the VR headset. So can you induce the size weight illusion through vision alone, if you like? We're not too interested in talking about the details of the experiment here, but just to sort of foreshadow some later questions. People picked up each of these objects in a randomized order in each of these 3 conditions, and gave a rating of how heavy the object felt by simply giving a number on every single trial. And then we normalized all of this to a Z-score distribution. So everyone's wacky rating scales are all normalized to the same size and the same shape and stuff like that. So we can kind of directly compare the magnitudes and the perceptual ratings and the magnitudes of the illusions that people are getting in these 3 different conditions. All right, and so this is what we find here. Now, this graph, I think, is a little bit busy. So what I'm going to do here is distill these 3 different conditions down into the different scores by subtracting the average rating given to the large from the average rating given to the small in each one of those conditions as an indication of the magnitude of the size weight illusion in each one of those conditions. And you can see here, looking at these plots, that, again, condition 1, where the information is congruent, looks like it's got that steeper slope that we were showing before, so a larger size weight illusion. But, you can look at this on the next graph here and see it even more clearly, that our condition 3 here, where we're just using visual feedback of the VR headsets, 3 identically sized objects that look as if they have different size, yields a very significant size weight illusion, but one that's quite modest, certainly compared to this tactile condition here that we have in condition 2, where people are seeing the same sized object, but picking up things that are physically different sizes from one another. And the largest one still is this condition 1, where we have congruent visual and haptic information. Both of the senses are telling us these objects are different sizes, and this yields the largest size weight illusion. So this tactile size cues, the ones experienced by your hands, they induce a stronger weight illusion than the visual size cues, which is in line with that Ellis and Lederman study. But you get the strongest illusion when the visual and tactile cues are combined with one another. The visual cues are not redundant, as suggested by the Ellis and Lederman's paper from 1993, but they're being almost perfectly additive in this context. So this is quite interesting, right? This is virtual reality is taking this old psychophysics paradigm where senses are being eliminated in some way and instead putting them in conflict to answer a question in a slightly different way and finding arguably something different than the original paper. We've also done some work along these lines with the material weight illusion, a related perceptual phenomenon where you have different materials of objects that look as if they have different weights, obviously, but all are adjusted to weigh the same amount. And when people pick these things up, they experience that the light-looking object, in this case, the polystyrene cube, feels slightly heavier than the heavy-looking object, the cube that looks as if it's made of concrete. And we were lucky enough to get a videographer in to create some slightly fancier videos of these paradigms in practice here. So I get to watch my colleague Sam Vine donning the VR headset and experiencing this paradigm for the first time. It was quite cool to capture a colleague experiencing this setup in my lab for the first time. Here you can see he's interacting with 3 different cubes that are all exactly the same. They're all made of corkwood, so they all feel like they have the same material properties. But as the camera pans around, you'll be able to see that what he's seeing through his VR headset is that they all appear to have different material properties. And we spent quite a lot of time here trying to find material properties that, struck that balance between looking like they were those different materials through the VR headset, which wasn't particularly high resolution at the time, but also, didn't feel too incongruent there. And this was work done by Caitlin Naylor for her undergraduate dissertation. This work was presented for the Experimental Psychology Society undergraduate project prize as well. So you can see Caitlin giving a video of this online on the Experimental Psychology website if you feel so inclined. But, just to step through this reasonably quickly, she had these conditions that pretty well mapped onto the previous size-weight illusion study. So ones where the objects all feel the same but look as if they're different, just like you saw in that little video back there. Situations where they all feel different but look as if they are exactly the same, so kind of the opposite. Conditions where things are congruent, so what feels like polystyrene also looks like polystyrene. And then that sort of missing final condition that we never had in the size-weight illusion experiment, but sort of wish we had with hindsight, this condition where we make things completely incongruent. So the thing that feels like it's polystyrene looks like it's made of granite, and the thing that feels like it's made of granite looks like it's made of polystyrene. So we can really see which of our senses win out in terms of this magnitude of the size-weight illusion. And again, with this graph, we've just plotted the magnitude of the size-weight illusion here across all of these 4 different conditions. And we can see here that there's a small but significant size-weight illusion in this visual differences only one. So they all feel the same, but they look as if they have different material properties. Making something look different in VR will affect how heavy it feels. Again, that sort of message being hammered home here. And perhaps to be expected, the condition where everything is congruent, they look and feel as if they're made of the same material, yields the largest material weight illusion. But, it's kind of these 2 conditions in the middle where things get really interesting, because once again, we see this situation where the tactile differences only, so they feel different, yields a smaller illusion than this congruent visual tactile experience. And one that's absolutely no different at all from this incongruent experience as well. It seems like you're almost completely ignoring the visual inputs when the tactile inputs are telling you something different in this context. So there's quite an interesting story to be told that we're still trying to figure out here, to do with when things are congruent and when things are incongruent, and at what point you reject the input from one of your senses. So there's quite some interesting stories to be told around all of that, I think. And very much a sort of work in progress. But I think there's still a pretty clear idea here that this summative effect of visual and tactile cues is only something that will appear under these certain conditions when they are, congruent or incongruent with one another. Okay, so we get these nice situations where tactile cues seem to dominate visual cues, but, well, you'll be thinking to yourself, well, these are pretty low resolution VR displays, right? Maybe in the real world, we believe our eyes, which are far, far higher resolution than we would the visual feedback delivered through a virtual reality headset. And this is entirely true. And, I think there's a piece of work to be done replicating these previous studies with, some 4K displays, things that get a little bit closer to the foveal resolution of the eyes. So, I guess stay tuned for that work as it comes. But these studies really serve more as a proof of principle for how immersive virtual reality can be used to do ecologically valid studies of perception. No longer are you constrained with a chin rest or a head rest or, a hand underneath a half silver mirror. People are interacting with these objects just like they would in the real lab space. And that's quite exciting for a research program like mine, where we're interested in examining how the weightings of different modalities might change during things like chronic pain or aging or fatigue. Now that I'm in a sports science department, I've become very interested in fatigue and heaviness and stuff like that as well. So, that's kind of the end of the main body of my talk, but I did not want to leave it here without talking about some of the ongoing work I'm doing related to hand tracking. And this is kind of a little bit off to the side, but I've become fascinated by this idea of virtual reality hand tracking. Typically, when you're interacting with real things in VR, you're doing so with controllers. All the stuff I presented before is sort of mixed reality. You're touching real things, but you're seeing stuff. In a usual virtual reality experience, you're using controllers or these days having your hands tracked. And this tracking of your hands can lead to some really pretty astonishingly powerful effects as far as I'm concerned. You instantly feel like you embody a hand that you are having tracked. And this lovely demonstration here from this hand physics lab setup, where you're just interacting with a mirror reflection of yourself, is one of the most astonishing things I've experienced in virtual reality. You really feel these phantom touch sensations of your fingers interacting with this mirror reflection of yourself. And there's no tactile feedback at all, but I guess it's something about the efferent copy and stuff like that that's matching on in such a profound, beautiful way that it really is a great experience. If you get a chance to try this out, I'd really recommend doing so. But we've become really interested in hand tracking from this embodiment perspective. And, I think that hand tracking from a number of perspectives is really quite a profound thing. But you can also create these really dramatic changes to participants' body shapes and sizes. Here I've made Sam's left hand twice as big as his right hand. And it's you just want to wiggle your fingers and experience this. But, even this one's really quite nice. What I've done here is I've extended the length of Sam's index finger twice as much. So he's now got a gigantically long index finger. And completely unprompted, he sits there and he just wants to check, is my finger really this long? Because you do feel like it's yours instantly. There's no induction period needed or anything like that. And I feel that hand tracking is a whole different level from anything else we've been able to do in VR with avatars and things like that. And this is something that Caitlin, who has now left my laboratory and is now working at the University of Bath with Janet Bultitude, but I'm involved in her PhD still, examining complex regional pain syndrome, sometimes called CRPS, which is this really distressing pain disorder that comes not just with really crippling pain, but a variety of disturbances of body representation as well. There's a couple of sketches here from different patients who have complex regional pain syndrome, but your hand can feel inflated, bits of the limb can feel like they're missing, there can be textural differences, and there's nothing kind of consistent about any of this other than the fact that the more profound the disturbance in the body representation, the greater the level of pain, suggesting that these two things might be related in some way. So Caitlin's PhD is really about seeing if she can use hand tracking to tackle this idea of body representation disturbances in complex regional pain syndrome. So here we've got the paradigm that she's developing for neurotypical participants, looking at this hand representation. And it's this sort of like weird quirk that our internal representation of our hand doesn't actually match up to our physical representation of our hand, the physical shape of our hands. Some really nice work by Patrick Haggard and Matt Longo have shown that, these two things start to diverge. So she's initially looking at whether hand tracking can sort of push people's hands closer or further away from their internal body representation and what impact that has. Before, doing some of the more ambitious work where maybe we can start to try and create some tailored virtual hands that map on directly to what individuals with CRPS's body representation disturbance looks like. So how participants feel their hands look and act. And here's just a variety of little demonstrations of things that I've knocked up in virtual reality to make stuff just feel a bit strange about some of these hands. It's the same hands being tracked and just changing the graphics that are overlaid atop these hand tracking things. And, I think there's some really sort of wonderful directions that we go in from here. At the moment, she's in this stage where she's doing some PPI work, chatting to patients with complex regional pain syndrome and getting a broad picture of what sort of individual differences in body representation disturbances they have, and ultimately what they would like their hands to be looking like as well, to see if this is a potential treatment, not treating the pain, but treating what maybe is the core underpinning disorder. The other things that I'm interested in drifting towards are, well, really the sort of fairly obvious stuff for someone like me who's interested in motor control, measuring the sort of fundamental behaviors in virtual reality, because we know really fleetingly little about what happens when we put on a virtual reality headset. Do we pick things up with the same forces? Do we open our hands as wide? And this is all work now that we're sort of getting to get set up in the lab. Some challenges to do, tracking the hands and interacting with objects in in different coordinate frames and stuff like that. It takes quite a lot of organization to do, but we're almost at the stage now where we can create this simulation, this facsimile of my research laboratory in virtual reality. And that becomes a really interesting set of experiments that almost write themselves. I'm quite excited about doing. I have another PhD student who's working in the context of chronic pain, but not from a body representation perspective, but from a active inference perspective. This idea that pain might be a mismatch between the internal and external states of the world that has somehow gone awry. And with virtual reality, it's actually quite easy to create these situations where you can move or change the distance of something quite differently. And here this sort of idea of this control display ratio where someone is rotating their hands over multiple trials, this supination movement that can be quite painful for someone with an elbow or wrist injury. And we're manipulating how far the physical hand goes compared to how far it appears the hand itself is going. So you can kind of imagine how those paradigms are going to start to unfold over the course of Joao's PhD here. And the last thing I wanted to talk about here, and I'm not even really going to talk about it, just kind of flag it up here, is the idea of remote data collection with virtual reality. And this came about as the work of Jack Evans, another PhD student in my lab, who is interested in tracking the upper limb movements and the improvements as a function of rehabilitation in stroke survivors who have some sort of hemiparesis or hemiplegia and are unable to draw a circle very well. Circle drawing is a sort of nice, easy task. But what we were able to do during the pandemic is send out essentially a motion tracking experiment to people with virtual reality to do in their own homes, individuals who already had an Oculus Quest headset in their house at this time. But the possibilities for taking these fairly low cost, it's about £300 for a MetaQuest 2 headset, into the clinics, into people's houses. I've had a master's student take one around southern India and take measurements of children with various different movement disorders in different schools. And working with these physiotherapists in this context, it's a really powerful and interesting way to not only improve the diagnostic speed of these sorts of things, but start to free up clinician time. So all of this is sort of signposted way, way into the future, but I just kind of wanted to give a bit of a flavor and an overview of the stuff that is exciting me at the moment with all of this virtual reality stuff. So yeah, thank you very much for listening. I've got more slides, obviously, and stuff like that, but I'd probably rather just stop it here and